This is video 25. In this part, we give the proof sketches of the thin path assembly lemma and the jail lemma. Both of these proofs use the window movie lemma defined in the previous video. We remind that the window movie lemma relies on two hypotheses. First, the path assembly should be long enough. Secondly, we need to find a vector v such that the width of the path assembly for the window wh for any integer h is bounded. We present here a result about thin path assembly. It will be useful at the end of the article to prove the shift lemma. Consider a simple path assembly P producible by a deterministic tile assembly system. This path assembly is thin if and only if it grows far more to the east than it grows to the north. In other words, a thin path assembly fits inside a rectangle whose length is far greater than its width. Consider the vector v of coordinates 0, -1. Then consider all the different windows wh. By the definition of the vector v, these windows are in fact vertical lines. Here we have drawn 3 of these windows in gray. For any of these windows, the width of P is bounded by the difference between the ordinate of the highest tile of P minus the ordinate of its lowest tile. Consider all the different movies of the path assembly P obtained with these windows. By definitions of a thin path assembly, we have a lot of non-empty bounded movies. In fact, the function phi used in the definition of a thin path assembly is defined to have enough non-empty bounded movies to conclude that the path assembly P is pumpable by using the window movie lemma. Thus a thin path assembly is always pumpable. Now, we prove the jail lemma. For the moment, we focus on bounding the width of a path which does not intersect with its translation by a vector v. Consider a vector v, an integer h, the window wh and its cut of the grid made of g2h and g2h plus 1. Let's the integer p be the period of the window wh. In this example the window is in gray, the coordinates of the vector v is 16, 0 and p is 16. Now, consider a simple extremum path p. This path is hatched. Without loss of generality, we assume that this path is positive. Consider the translation of the path P by the vector v. This new path is called Q. Note that the paths P and Q do not intersect. Our aim is to bound the width of the path P by 2 times P square plus P. Here, we only give a proof sketch. The article available online deals with all the technical details. Consider the decomposition of the path P in extremum arcs in G2H. We obtain 4 arcs A1, A2, A3 and A4. Also consider the dual decomposition of the window WH. Remark that the width of A4 is strictly greater than the width of A3 and that the width of A3 is strictly greater than the width of A1. Our aim is to find such a subsequence of arcs of increasing width. We now explain how to proceed. First, since the path P is positive and extremum and since the first position of the path Q is the first position of the path P translated by -v, then the first position of Q always belongs to the dual segment E0. In this example the last position of Q belongs to a dual segment, in particular it belongs to the dual segment E3. This second remark is not always true. The article available online deals with the case when the last tile of Q does not belong to a dual segment, but this other case is similar to this one. Now, note that the path Q starts in D0 and ends in D3. Then by the result of video 17, the arc A1, A2 and A3 are dominated by the path Q. More precisely, consider the decomposition of the path Q in extremum arcs. We obtain 4 arcs A'1, A'2, A'3 and A'4. Remark that arc A1 is dominated by arc A'3 and that arcs A2 and A3 are dominated by arc A'4. Now we explain how to extract the sequence of arcs of increasing width from the decomposition of the path P. We start by defining the arc A2 as the arc A1. The arc A1 is dominated by the arc A'3. Since the path Q is the translation of the path P by the vector V, then remark that at A'3 is the arc A3 translated by minus V. We define the arc A2 as the arc A3. Remark that the arc A3 is dominated by the arc A'4. Since the path Q is the translation of the path P by the vector V, then remark that at A'4 is the arc A4 translated by minus V. We define the arc A2 as the arc A4. In this case, we have built a sequence of arcs such that for any integer I, the arc A2 translated by minus V dominates the arc A2 I minus 1. Thus the width of the arcs of this sequence is increasing. Finally, if the width of the path P is larger than 2 times P square plus P, then it's possible to prove that the length of this sequence is larger than P over 2. In this case, the width of the last arc of this sequence is at least P, and this arc would intersect with its translation by minus V, which is a contradiction. Then the width of the path P is bounded by 2 times P square plus P. Now, we conclude the proof of the jail lemma. First, we resume the jail lemma. See videos 7 and 8 for more precise definitions. Consider a path assembly P which satisfies macroscopic conditions and which is producible by a deterministic tile assembly system. Here, the seed is in black. Also consider a vector V whose norm is bounded by B2. The definition of this bound is available in the article. We consider a distance delta and an index I1 such that the seed and the segment of P from its first tile to the index I1 belong to the square of width delta. Now consider the following index I2 such that the tile of P at index I2 is not inside the hashed square. Suppose that the segment of P from index I1 to index I2 does not intersect with its translation by minus V. Then we can consider the path assembly Q, which is the segment of P from index I1 to index I2. Remark that the length of this path assembly is at least the distance between the two squares. Also, the path assembly Q is producible from a new seed made by the previous seed and the segment of P from its first tile to index I1. This new seed is in black and it belongs to the square of width delta. Thus, the size of this new seed is bounded by delta plus 1 square. For any integer h, consider the window WH associated to the vector V and the extremum arc extracted from the path P for this window. The width of this extremum arc of P is the width of P. By the previous reasoning, the width of the path P is bounded. The window movie lemma allows us to conclude and to prove the jail lemma.